Okay, so in this video we're going to start talking about what happens to materials when force is applied to them. So we're going to start off by talking about Hooke's law. Hooke's law is named after Robert Hooke. He is the same guy that studied springs and came up with the spring constant, and this is really similar to that. He's also the guy that was enemies with Isaac Newton. But this K value here is sometimes called Hooke's coefficient. With springs, it's a spring constant, and but the same thing applies to other materials as well. So I'm getting a little bit ahead of myself. Let's back up and talk about what this statement means. It's saying that the force applied to an object is proportional to the change in length. And if we put this coefficient in front of it, we can actually come up with an equation that the force applied is equal to K delta L. So we have this bar that is some length, and then we hang a mass from it, which applies a force to it, and it increases the length by some delta L. How can we know how much that delta is? Well, if we know what the material is, we would know what its coefficient is, and then we just could use this equation to calculate delta L using the known force and the coefficient, or we could calculate the force required if we know the change in length and the coefficient. So basically we just have these three variables and we can solve for any one of them if we know the other two. So let's talk a little bit about the relationship between force and elongation. So materials that have a relationship, a linear relationship, where you apply a force and you get a certain amount of elongation. This part of the graph here is following Hooke's law. Okay, so there's a slope to this part of the graph. The steeper the slope, the stiffer the material. But regardless of its steepness, if it's a linear line, it's indicating a direct proportional relationship between the amount of force being applied to an object and how much it elongates or stretches. So Hooke's law holds true for relatively low forces, except at some point it's going to begin to curve a little bit. That's where we are said to reach the proportional limit. So this proportional limit, this linear relationship no longer holds, and it starts to curve a little bit. Then we reach what's called the elastic limit. Elastic means that if we remove the force, the shape will go back to its original size. Once you exceed this elastic limit, it doesn't do that. It will perhaps bounce back in a way that's parallel to the original line, but you're going to end up with some amount of permanent elongation. So you just basically stretched it out too far. Then most materials have this plastic region where the material stretches out quite a bit, a lot of elongation with a relatively small amount of force being applied. So it just begins to stretch and stretch and stretch more. It begins to neck in this area is why it goes back down. The material begins to get smaller in cross-section, kind of like an hourglass. And that smaller cross-sectional area is what leads to this going down, smaller force, and then it breaks. Right here's the rupture or fracture point where it just breaks. Okay, so that's important because if I jump back here, this original part of the graph, this linear part, this elastic region, we can get some information from the material based on that elastic region. So first of all, stress, we're going to use sigma to denote stress. Stress is equal to force divided by area. So we have some force applied over a circular area. We divide it by that area, and it gives us stress. In English units, it would be in PSI, pounds per square inch. In metric, it's going to be in newtons per meter squared, are the units we will use. So just like, if I jump back here again to this, just like we had force and elongation, if we, the same type of graph can be made for stress and strain. So strain is similar to elongation, but strain is a ratio. What strain is it's a change in length. So it's a delta L, a change in length, compared to the original length. So if I had a bar that was, I don't know, a meter long, and I stretched it out, and it stretched out another 0.1 meters, then the strain would be 0.1 divided by 1, or just 0.1. So it's a comparison, it's a ratio to the elongation part to the original part. So it's unitless because we're taking units of length, meter, divided by meter, and then those just cancel out. So stress divided by strain, if we look at that stress-strain curve, the ratio or slope of this line gives us stress over strain. Stress, we got strain, and as I said, a steeper slope means a stronger, well, I shouldn't say stronger, but a stiffer material, and a more gently sloping line indicates a less stiff material. But this slope can be described by this capital E. This is known as Young's modulus, or the modulus of elasticity. It's stress divided by strain, sigma over epsilon. And this varies for different materials. As I said, stiffer materials will have a higher E value. Less stiff materials will have a lower E value. But these different formulas in combination can help us calculate things. So we've got stress is force over area, strain is change in length over original length, and modulus of elasticity is stress over strain. Let's use those to answer this question. We have a piano wire that is 1.60 meters long, and it has a tiny little diameter of 0.20 centimeters. Now we like to deal in meters typically. So I think the first thing I would do is convert that from centimeters to meters. So 0.2 centimeters, I'd have to move this decimal place 2. That'd be 0.002 meters. Okay, and that's the diameter. How great is the tension? So tension is a type of stress. It's asking us to find what is the stress if the wire stretches 25 centimeters when tightened. So we're assuming it's in a relaxed state here. Then we're going to stretch it out another 0.25 centimeters. That's going to be our delta L. Okay, so what is the stress going to be? Well, let's first find the area. It's a circular area. Area of a circle is pi d squared over 4. So this is pi times 0.002 squared over 4. And that should give me 3.14 times 10 to the negative 6th meter squared. It's a really small number, but that's because we're dealing with a relatively large unit of area for something that is pretty small. It's a little piano wire. So that's our area. Strain is equal to the delta L over the original L. So the delta L was 0.25 centimeters, and the original length was 1.6 meter, 0.60 meter. So I need these to be consistent units. So let's move this 2 decimal places, 0.0025 meters over 1.6. So that gives me a strain of 0.001562.5. And there are no units on that. Strain is unitless because it's just a ratio of lengths. I've got meters and meters. They cancel each other out. I'm left with this unitless strain. The material, we're told, is steel. So that means that we can look up its modulus of elasticity. This should be in the textbook. Let me check real quick to see where that is. Okay, this can be found in table 9.1 in the textbook. And for steel, the modulus of elasticity is 200 times 10 to the 9th newtons per meter squared. So if modulus of elasticity is equal to stress over strain, and we know the strain and we know the modulus of elasticity, we can calculate the stress. The stress is going to be equal to the modulus of elasticity times the strain. So the stress is equal to 200 times 10 to the 9th times the strain of 0.001562.5. And so the stress is equal to, okay, looks like I'm getting a pretty big number here. I'm getting 3.125 times 10 to the 8th. Times 10 to the 8th. Okay, let's take this over to the next slide. Let's actually pick right up where I left off on that previous slide. Strain is 3.125 times 10 to the 8th. Okay, that's a really big stress, but we've got a little tiny area, so the force may not be so big. And so our area was 3.14 times 10 to the negative 6th. Our area, let me write that down, area is 3.14 times 10 to the negative 6th. And if stress is the force divided by area, and we want to know force, then the force is just going to be equal to the stress times the area. So the force is going to be 3.125 times 10 to the 8th, which is a really big number, times 3.14 times 10 to the negative 6, which is a really small number, and that equals 981 newtons. It looks like I'm about out of time, but I think I've finished this problem, so we'll pick up on the next video.